Welcome. In this video, we're going to begin to talk about radiation detection. This is primarily because we now have enough physics to appreciate the principles employed in how we detect radiation. Well, you might wonder, why do we need to detect radiation? Of the many reasons we might want to detect it, two or three reasons stand out the most. After we have studied, we have exposed a certain anatomy of a patient, we would like to obtain that information, we'd like to obtain the x-rays. So in this case, it is paramount that we know how to retrieve that information. So radiation detection is important when it comes to the formation of images. The reason why we set out to even to study a certain anatomy of a patient. The other reason has to do with our bookkeeping. Because radiation has also negative effects on the biological organism, it is quite useful for us to know how much radiation a patient is exposed to, not only a patient but also a technician. So we need to know the dosages that a person will be exposed to. So we need to be able to detect how much radiation was produced, because it has to be absorbed by something or someone. If you were in a certain vicinity, you would also be exposed to radiation. And this allows us to manage the safety of our studying of radiography, that is. So these 2 or 3 reasons are very, very good motivation for us to look at the principles of radiation detection. Well, there are a few desired properties of a detector, of a radiation detector. And as I've mentioned, there are many, but I've chosen these few because they might be more accessible to a lot of us. So number one, we want our detector to be very efficient in absorbing radiation. This is quite useful, obviously, because that means we won't have a miscount into how much radiation was truly how much radiation was there to begin with. If our detector is not efficient, it means some radiation might go unaccounted for. So we want our detector to be very good at absorbing. And because typically we don't deal with X-rays directly, we convert it to some useful signal, sometimes visible light, sometimes electrical signals. We want our detector to be able to absorb radiation, X-rays, and quickly convert it to the desired signal. And in the process of conversion, to have minimal losses. Because we're converting from X-rays to possibly physical light or electrical signals, we want our detector to be very efficient in that conversion. We want to have as little data loss as possible. And when you have a sequence of exposures that you are doing, you want your detector to also be quite good in its ability to absorb, or rather to be ready for the next absorption or for the next study. So we want it to be responsive as far as time is concerned. Some radiators or some detectors are not very good at this. For instance, the olden days, the phosphors, they were very poor at being used for a sequence of exposures, because they'd have a long afterglow. That is, when the electrons were excited to a higher energy state, they would fluoresce for a very long time, which means you cannot conduct another exposure immediately after. So with us, we would like to have a detector that is quite good, quick at responding. In particular, when you're dealing with fluoroscopy, where you want to take a series of shots, series of frames, you want your detector to be ready for the next frame. Okay, and obviously one other desired one is to have a detector that is able to catch a wide range of radiation. Of course, when you're dealing with a particular anatomy, you know what kind of output radiation to expect, but the wider the range, the better. And a wider dynamic range means the contrasts between the different types of radiation is going to be much more defined, which means our pictures are going to be much more clearer. Okay, so these are kind of the few desired properties of a detector that I thought would be quite, might strike a chord with us. Okay, now let's get into the detectors themselves. There are many kinds, but I will focus on two, possibly a third one later on, depending on how time goes. But the first basic one is the ionization gas chamber. Well, some people like to have an S there, depending on what kind of spelling you have. But anyway, the ionization gas chamber. And as the name suggests, that this detector uses the removal of electrons from a stable atom. That's the idea behind it. That's the major idea behind ionization gas chambers. They need not be gases, but the idea is that there's going to be some kind of ionization of some neutral atom, and that kind of radiation, or rather that kind of ionization, is going to give us an idea of, or will trigger for us that we have absorbed some kind of radiation. And the other one is, these are scintillation crystals. Essentially, these are phosphors. These are crystals or semiconductors that emit light whenever they are excited or whenever they receive some amount of excess energy. Okay, then let's look at how ionization chambers work. So the setup is as follows. You have a chamber, which here is signified by this shell. The chamber is filled with a stable gas. Again, this means our gas is neutral. As far as charge is concerned, it's neutral. And inside of this gas chamber, which is filled with a gas, there is a positively charged wire. This positively charged wire will serve as an anode, and the shell, this outer shell, serves as a cathode. That is negatively charged. Because the wire is positively charged and the shell is negatively charged, there's going to be an electric field between this anode and this cathode. And that electric field produces some kind of a voltage, a potential difference between the two. And you might begin to imagine that if we were to introduce some kind of a particle here that's charged, that has some kind of a charge, that particle will either be attracted to the negatively charged shell or the positively charged wire or the anode. And that's exactly the idea that is employed in ionization chambers. You have radiation coming in through a window, and this radiation comes in and would interact with the gas molecules that are inside the chamber. Because this radiation is ionizing, which means it's going to remove electrons from the stable gas, these electrons are going to be drawn, these electrons that are ionized, that are removed from the gas, they're going to be accelerated toward the wire, which is positively charged. The wire is positively charged, the electrons are negatively charged, so there's going to be a force of attraction. And they're going to be absorbed over here. And this flow of electrons through the positive wire will trip a voltage change, or there will be a flow of current. So the more radiation we have here, the more electrons will be released to the wire and the more current will flow. This is the idea behind an ionization chamber detector. It's that the amount of radiation is proportional to the current we detect. So this is the setup, and I've actually kind of jumped the gun and explained what this slide was intended to address. Again, the basic idea is that you have a gas inside, and this gas has particles or has electrons, and when radiation comes in, it's going to interact with the gas molecule, ionizing it. Remember, ionizing means to remove electrons. These free electrons are going to be inside of a electric field. The electric field is going to attract them toward the positive side of the electric field. That's on the anode side, the wire. When they're drawn to the wire here, they're going to therefore flow through this circuit. And if we have a voltmeter here or even an ammeter here, we can detect the flow of current. We're going to pick up the flow of current, and that flow of current was going to be proportional to the amount of radiation we receive here. The more radiation we receive through the window, the more current is going to flow through the circuit. And that's how we would detect the amount of radiation. Of course, this is limited in its dynamic range because the amount of radiation we detect must be of the ionizing kind for that particular gas. If the radiation doesn't ionize the gas, then we would not pick up this flow of electrons. No electrons would be removed from the gas. So this ionization chamber detector, you might imagine, does not have as wide a range as, well, maybe I shouldn't say as anything because we don't have anything to compare it with, but the range is going to be limited to what are the ionization energies of the gas. So by using the appropriate gas, you can cater for your whatever window of range you're interested in. Okay. Then the other kind of radiation detector is what we call a scintillation crystal. And scintillation here just means a phosphorus or light emitting. And we saw this when we spoke about semiconductors, that semiconductors, they have this ability of absorbing radiation so that electrons are excited to the conduction band. But then when the electrons return from the conduction band back to the valence band, there are possible routes through which they could take. They could either take they could either be trapped on the electron traps, or they could go through the phospholuminescent center, the luminescent center. And if they go through the luminescent center, they're going to radiate visible light. They're going to produce visible light. So that's what we mean by a scintillator. It's just a phosphorus substance that is a light-emitting substance when it's excited by receiving extra electrons. Okay, so that's the basic idea, is that the atoms of this crystal, this scintillating crystal, are easily excitable, and when they de-excite, that is, they return to their ground state, they will emit light. And of course, the most common kind are the solid types of scintillators. And as to how we classify scintillators depends on what we do with the light. Sometimes the light produced by a scintillator is sent to what is known as an intensifier, an image intensifier. That would be used for a different application. And sometimes the light produced is used for a multiplier, photodiode multiplier, that will also have its own advantages and applications. So let's consider the light produced by a scintillating crystal when it's coupled with an image intensifier. Okay. So an image intensifier, this is on the right-hand side here. We have a schematic of it. Don't worry about the labels. The important ones I will highlight. The important labels on this diagram I will highlight. So the idea again is our detector receives incoming radiation, and this incoming radiation interacts with the phosphorus substance or a scintillator. Remember, a scintillator is going to receive radiation. The electrons of it will be excited, and these electrons will be excited to a higher energy state, the conduction band, but then they will de-excite because they are unstable. They will de-excite, and their route of de-excitation will cause light to be emitted. And this part here, this first layer, maybe I should use a highlighter to distinguish it. This first layer here, this green layer, that is our scintillator, which here has been labeled as an input phosphor, or you could think of it as an input scintillator. It's the part that absorbs the incoming radiation, and it gets excited and then will release light. But this light released from the green layer is directed toward what I will highlight as blue, this blue part here. This is a photocathode. A photocathode is nothing more than a substance which is very sensitive to light. When it receives light, it will produce electrons. That's what a photocathode is. It receives light produced by the input scintillator, and as a result, it produces electrons. But then these electrons produced from here, they are under an electric field. Sometimes we call this a focusing electric field. What it does is, because these electrons are negatively charged, that means we can manipulate their direction. That's the beauty of electrons. They have an electrical charge, so we can manipulate their path of travel. And that's why these electrodes, they are focusing. They focus the electrons toward some center, or some quote lens, if you like. But not only are they focused, they are also accelerated. They're sped up, which means if they had some energy here, let's say 2 volts, 2 kilovolts, they're going to gain a certain amount by the time they reach this region here. And this region I'm holding out, but I should mention it's called an output phosphor. This is again another a scintillating substance or scintillating crystal, which will therefore receive the electrons, and because it's received electrons which are exciting it, it's going to produce light. That's the key. It's that we had a certain amount of incoming light, maybe incoming radiation. This radiation is converted to light, and this light is used to excite electrons, to produce electrons from the photocathode, and then the photocathode releases these electrons, which are therefore sped up towards some focal point of our interest. And then at this focal point, these electrons are therefore used to produce light again. We have an output phosphor here. This output phosphor will produce light when these electrons strike it, and that light can therefore be observed. We could use lenses, all kinds of geometric ways of actually observing the light from this side on. But the key here is the electrons are going to gain speed. They're going to gain energy, which means the electrons that are going to strike the output phosphor will have a little more energy, which means the light produced here is going to be brighter. This is what image intensifiers do. They actually improve the brightness of your image. So the light produced here, it's still proportional to the incoming radiation, but it's brighter. That's the key. And this enables us, at least in our practice, to minimize the radiation we expose our patients to, because no matter what we gain here, we can always intensify it over here so that it's visible to our eye. Okay, those are image intensifiers, and this is where input phosphor or scintillating crystals are used. That's one context. The other context where scintillators are used is with a photodiode multiplier. A photodiode multiplier, I think the best way for me to explain it is to use LEDs. All of us are very familiar with LEDs, I would imagine. LEDs are what we call light-emitting diodes. These are diodes which, when you run current through them, they produce light. Photodiodes are the opposite. They are diodes which, when you shine light on them, they produce electrons. I hope that that's clear. LEDs, they produce light, so they take electrons, they take current, and what they give you is light. Photodiodes, on the other hand, they do the opposite. What they do is they take light, and they produce electrons for you. And these electrons, because they're electrons, essentially they're flow of current, and we can manipulate that flow of current to our liking. Okay, I hope that's a very a helpful approach to it. So in this context, again, we would have a scintillator or a phosphorus substance, a substance that emits light whenever radiation hits it. Over here, I have a schematic of it. We have some input, scintillator over here. Incoming radiation strikes it, but because this guy is easily excitable, when radiation hits it, it's going to produce light, or if you like, its electrons are excited, but then when the electrons de-excite, they produce light. This is what this light is. But then this light is directed toward a photodiode. Remember, a photodiode absorbs light and produces electrons. So this here is a schematic to show you, or it's a stand-in for what a photodiode is. Of course, a photodiode is a lot more complicated than the scheme here. The idea is just to get to show you how radiation detectors with the photodiode works. That's the main purpose here. It's not to fully understand how photodiodes work. We will have a discussion of it later. Okay, so this is how scintillators work. Scintillating radiation detectors. This is how they work. At least this one is coupled to a photodiode. And this current here can be manipulated. It can be converted to physical light. This is where we can generate even digital images, because we can assign some kind of a scheme. That is, a certain amount of voltage can be assigned a certain color, and we could essentially build an image using this output current here. This is how scintillating crystals are employed in the context of radiation detection. Okay, I hope this was insightful. Later on, we will talk about another kind which is very useful when it comes to digital radiography. That's a large field detector, LFD. But for now, I will conclude the video here. I'll see you in the next one.